Alright, welcome back. Today we'll be looking at vector spaces. And to define a vector space, it's basically a collection of objects which we'll call vectors. And the set of those objects is denoted by this V. And the thing about this is, just like fields, there is an associated addition and a multiplication operator. And that is what we'll be looking at. Those are the main operations, and they also follow a certain set of rules, just like fields. Now, a field was a triplet, so it was associated with a set of objects f, a plus, and a dot, the addition and multiplication. But in case of vector spaces, it will be associated with a set of vectors v, a set of scalars, which happens to be a field, that is f, the vector addition, and the scalar multiplication, that is a scalar from the field f multiplied with an object that is a vector from the vector space V. So that's what a vector space is. Now, in general, the vector space is denoted as V of f, that is a vector space over the field f. So notice that the field over here, that is f, is a crucial component of the quartet, and so we write it as V of f. Now the valid operations that have been defined are for any vectors u and v and any scalar. So if I'm mentioning a scalar, it belongs to the field f. So any scalar f, u plus v, that is what vector addition is, and f times u, that is scalar multiplication. Both of them are binary operations. Now the components of a vector space, as I mentioned before, it's a quartet, so there will be four components. V is the vector space, or the set of vectors, I'm sorry. F is the field of scalars, so it also comes with, although I write f, it also comes with its own plus and dot. Okay, and now vector addition is there, that is denoted by plus as well. So whenever I'm writing plus or dot, depending on the operands, please do figure out what sort of which plus and which dot that is. Okay, so I'm denoting the vectors as with a bar on top of it, and scalars are plain letters. So please be mindful of which plus and which dot is being used. So f is a field of scalars, plus and dot are the vector addition and scalar multiplication. They are operations on the vectors. Okay, now let's move on to the definition. As I said before, a vector space is a quartet, also denoted as V of f, and it is only a vector space if it follows the rules that are given below. So just like fields, even vector space has 6 rules, and the first of them is closure. So in fields, closure was a plus b belongs to f, and a times b belongs to f. So similarly, in vector spaces, u plus v, the sum of two vectors, is a element of the set v, and f times u, that is the multiplication of a vector and a scalar, is also an element of the set of vectors v. Okay, that closes the closure. Now commutativity is the same as before. It's nothing different. If you have two vectors, then u plus v is the same as v plus u. The order of operands in the vector addition don't matter. Similarly, if you also have a scalar f, f times u is the same as u times f. So even in scalar multiplication, the order of the operands doesn't matter, but one of the operands has to be a vector and the other has to be a scalar. That's a given. Associativity. If you have uvw that are vectors and fg that are scalars, so two associative rules are there, one for the addition and one for multiplication. The addition associativity is, if you have to sum up three vectors, then it doesn't matter which order you do it, whether you sum v plus w, evaluate that, and then add it to u, or if you sum up u and v, evaluate this, and then add it to w. So it does not matter. It's the same as associativity of addition in fields. For multiplication, if f times g times u is to be evaluated, then either you can evaluate g times u first, then you can multiply that with f, or you can evaluate f times g first, then multiply that with u. It will give you the same result. Going on to identity. So in this case, there is only one identity because no multiplication of two vectors is defined, and the multiplicative identity is played by the multiplicative identity from the field f. But there is a separate additive identity for two vectors, and that is denoted by the 0 vector. So as you may expect, for any vector u plus 0 is the same as u. So this is the additive identity for the vector addition, that is 0 vector. Now similarly, for scalar multiplication, 1 from the field f is the multiplicative identity. So if you multiply any vector with 1, you will get the same vector again. That's the rule. Inverse. So again, there is no multiplicative inverse that is inherited from the field f, but there is an additive inverse, and it exists for every vector u, and obviously u plus minus u will be the 0 vector. That's the definition of the additive inverse. And now moving on to distributivity. Distributivity is also the same. If you in fact there are two distributivity rules over here. In the fields there was only one. So if you have two vectors u and v and a scalar f, then f times u plus v will give you f times u plus f times v. Okay, the multiplication is distributed inside the parentheses. Now if you have f plus g, f and g are scalars. If you have f plus g times u, u being a vector, then this multiplication over here is distributed over the addition. So this will give you f times u plus g times u. Alright, so this is what the next thing you have to memorize is. I mean, you don't need to memorize this. If you have already memorized the rules for fields, as I told you, this actually should be easy. It's not that difficult. There are just probably a few extra rules in the distributivity, but otherwise it's actually very similar, not that different. Alright, so in the next video we'll be deriving the properties of the vector fields directly from these rules. Okay, until then, stay tuned, see you later.